we have a series of short talks. Marcus Rao will be first. Marcus, is this a pre-recorded? Oh, you're online. Great,
No,
hello.
I'm live. Okay, let me just
Great.
share my screen. All right. Thank you so much for giving me the opportunity to very briefly talk about this project that we are doing here at Argonne on optimizing the galaxy sample selection for weak lensing cluster mass measurements. So very briefly, of course, the accurate estimation of weak lensing cluster masses is very vital for future surveys like LSST. But for LSST, we have one big challenge, that is that we push to very deep observations, and we also decrease the statistical uncertainty in the measurement of cluster masses significantly, because we have very large areas of observation and a lot of galaxy background galaxies, source galaxies. The most important quantity to estimate in the context of cluster masses is, of course, the critical surface density that relates linearly with the measured cluster mass. And one of the big challenges that we have in modeling and estimating sigma crit is, of course, estimating the photometric redshift distribution of background galaxies, especially in photometric surveys where we have only broadband observations to do so. So essentially what you see here in the top panel is the process that we are looking at. We need to deconvolve essentially the noisy photometry of galaxies to recover the true line of sight distribution of the source sample, and then we can measure we can estimate the critical surface density that then relates to the cluster mass. The main problem is that this is an inverse problem. For optical surveys, we often have a significant photometric redshift error that leads to very poorly conditioned inferences. So what's showing here on the right-hand side is essentially the smeared out redshift distribution from observations of broadband photometry, and we need to deconvolve this into the true redshift distribution, and you have this inflation of variance that has very poor theoretical guarantees. So we have the problem of a deconditioned problem that has also very complex selection functions that we need to model to have a strong sensitivity for our inferences to model misspecification errors. So what we are doing in this project is we essentially trade off signal to noise in cluster mass measurements with the expected model misspecification error that we have from, for example, misestimating the spectral energy distribution of galaxies, or doing having biases in our population inference. What we do in this context is we take the observed photometry, we use a very fast variation inference technique to deconvolve the noisy observations into a latent parameter space of redshift galaxy type, etc., and then doing an optimization of the selection in this latent space. What we are able to do in this way is we can select source galaxy samples that have a very low expected photometric redshift error. And what you see here on the left-hand side is that in this way we can reduce significantly, by orders of magnitude, the systematic in our critical surface density modeling, while at the same time retaining the vast majority of our source galaxy samples. So so we are currently testing this approach, but also apply to LSST. Thank you.
Thanks so much. Let's thank our speaker quickly and move right on.